Scott McNeely didn't walk into the SPARC lab like a man checking on a side project. He walked in like a gambler, pushing all his chips to the center of the table. According to people who were there, he looked over this tiny, overworked team and said flatly that their chip, this unproven academic-sounding RISC thing, was going to take Sun Microsystems from a $500 million company to a billion-dollar company. This wasn't motivational poster talk. In 1984, Sun was a scrappy workstation vendor living off other people's silicon. If their homegrown processor failed, so did the roadmap for the entire company. The chip didn't even have a name yet. When marketing finally landed on SPARC, Scalable Processor Architecture, someone noticed the unfortunate detail that SPARC spelled backward is craps. The team was very explicitly told, do not say that word ever, especially not anywhere MIPS engineers might hear it. Behind the dark humor was a very real risk. They were ditching the dominant CISC approach, the received wisdom of the industry, for a stripped-down instruction set cooked up in university labs. Plenty of people, inside and outside Sun, thought this was a cute experiment at best. Over the next 2 decades, that experiment would power everything from engineering workstations to giant Unix servers and even space hardware. So the question for this autopsy is, how did a minimalist, almost academic architecture become the backbone of serious enterprise computing? And what exactly did Sun get so right with SPARC? To understand why SPARC mattered, you have to understand what it was rebelling against. In the late 1970s and early 1980s, CPU architects chased performance by making instructions ever more complicated. Complex instruction set computing, CISC, tried to cram as much semantic work as possible into each opcode. Need to copy a block of memory, operate on it, and update flags. There'd be a Baroque instruction for that. In theory, more work per instruction meant more work per clock. On paper, it was elegant. On silicon, it was ugly. Implementations required big chunks of microcode, instruction decoders that looked like small state machines, and pipelines that were hard to push to higher frequencies. Meanwhile, a quiet rebellion was brewing. At IBM, the 801 project had already shown that a small set of simple instructions, executed very quickly from registers, could beat fancier designs on real workloads. But 801 stayed mostly inside IBM, feeding into later products with little fanfare. The louder mutiny happened in academia. At UC Berkeley, David Patterson and his team built RISC-1 and RISC-2, brutally simple load-store instruction sets, fixed-length encoding, and an obsession with hitting nearly one instruction per clock. No multiply, no divide, minimal addressing modes. If the compiler couldn't make it fast, they weren't going to fix it with more opcodes. Down the road at Stanford, John Hennessy's group was doing similar work that would become the MIPS architecture. 2 flavors of the same idea. Let hardware be a fast, dumb engine. Push structure into the compiler and software. In this context, SPARC wasn't some random invention. It was very consciously a commercial descendant of Berkeley's RISC work, RISC-1 and 2, taking that experimental, provably efficient philosophy and betting the future of a real company on it. When Sun Microsystems entered the scene, they weren't a CPU company. They were a workstation vendor building Unix boxes for engineers and scientists, and their early systems used Motorola's 68000 series CISC chips. The 68K was a solid, elegant architecture, but by 1984 the numbers were becoming uncomfortable. Workstations lived and died by price performance, and the conventional CISC roadmap wasn't scaling the way Sun needed. Competitors were eyeing RISC prototypes. Motorola's own RISC efforts were, at best, uncertain. Sun's leadership, including co-founders like Andy Bechtolsheim and Bill Joy, could read the tea leaves. If RISC really did deliver more MIPS per transistor, the first workstation company to ship a credible RISC box would own the performance narrative. Waiting for a merchant RISC chip meant giving someone else control over your fate. So Sun made what looked from the outside like a reckless decision: build their own 32-bit RISC processor in-house. A small team was assembled, with Robert Garner as lead architect. They weren't Intel, they weren't IBM, and they certainly didn't have those companies' fab budgets. What they did have was a clear technical hypothesis from Berkeley RISC, a product line hungry for speed, and executives willing to let a workstation company pretend it was a CPU house. Culturally, it was a collision. Hardware traditionalists still trusted CISC. Software people were excited but nervous. If the new chip wasn't compatible with anything, the whole software stack had to be ready on day one. And in the middle sat the SPARC team, being told their success or failure might literally double or crater the company's revenue. The first SPARC implementation, what we now call SPARC V7, did not try to impress anyone with features. It tried to hit its performance target with as little silicon as possible. The initial chip was built as a roughly 20,000 gate array. That's vanishingly small by modern standards, and even modest for the time. It famously shipped without hardware integer multiply or divide. If you wanted to multiply two numbers, you burned a little loop of adds and shifts. Yet on real code, it cranked out on the order of 10 million instructions per second, about 3 times what contemporary CISC processors managed. The trick wasn't individual instructions doing more. It was getting very close to one instruction completing every clock cycle. SPARC took the classic early RISC route, fixed-length instructions, a clean load store design, simple addressing modes. The pipeline could be shallow, predictable, and easy to clock faster as processes improved. One visible quirk inherited from that RISC era was the branch delay slot. Every branch instruction was defined to execute the instruction immediately following it before the branch took effect. Compilers could use that slot to do something useful, like a calculation, instead of stalling. It complicated compiler backends, but in hardware it simplified the control logic and helped preserve that near one instruction per cycle ideal. This wasn't missing features because we ran out of ideas. It was a deliberate discipline. If a feature made the common pipeline path slower or more complex, it was suspect. The silicon budget went not into clever one-off opcodes, but into the core engine that could run ordinary instructions quickly and predictably. If you want to see where SPARC really diverged from most contemporaries, you look at its registers. Most architectures expose a fixed set of general-purpose registers, say 8 or 16, and lean heavily on memory for passing arguments, saving temporaries, and managing call stacks. SPARC's designers looked at that overhead and decided to attack it head-on. The architecture defines a large physical register file, at least 72 64-bit registers in V9, and in some implementations up to over 600. But at any moment, software only sees 32 of them as general-purpose integer registers. Those 32 are split into 8 global registers, G0 through G7, and 24 windowed registers. G0 is hardwired to 0, a trick borrowed from other RISC designs, useful for simple clears and comparisons. The remaining globals are true registers visible to all code. The 24 windowed registers are where the magic happens. They're grouped into register windows that slide up and down through the physical file as functions call each other and return. Each window presents 8 in registers, 8 local registers, and 8 out registers. When a function calls another, the hardware advances the window. What were the caller's out registers become the callee's in registers, instant parameter passing, no memory traffic. The callee gets its own fresh set of locals while still seeing the arguments in the inset. On return, the window slides back, restoring the caller's locals without touching RAM. Adjacent windows overlap in those in-out regions, so data flows down the call chain with almost no loads or stores. Local variables that would live on the stack in a conventional architecture just sit in registers across multiple calls. The spec allows between 3 and 32 windows to be implemented. That's a crucial scalability knob. A high-end server SPARC can implement many windows, letting deep call stacks run almost entirely in registers. A small embedded SPARC can implement only a few windows to save silicon, yet it still runs the exact same non-privileged instruction set. The OS can spill and fill windows to memory on overflow, so software stays portable. The net result is that one of the most common forms of overhead in real code, function prologues and epilogues saving and restoring registers on a memory stack, gets dramatically reduced. Compilers can generate straightforward high-level code without elaborate hand-tuning, and the hardware quietly turns that into a very efficient pipeline of register-to-register operations. All of this would have been a nice academic story if the shipping machines had flopped. They didn't. In 1987, Sun introduced the Sun 4 line, its first SPARC-based workstations and servers, replacing the earlier Motorola-based Sun 3 systems. This was the real market test. Customers buying these boxes weren't doing it to support RISC as an idea. They needed serious performance for CAD, chip design, and scientific workloads. The numbers, performance per dollar especially, were compelling enough that the Sun 4 line quickly carved out a dominant share of the Unix workstation segment. For many engineers in the late 1980s, a SPARC station became the default serious desktop. Inside Sun, the impact on the business was exactly what McNeely had wagered. SPARC workstations and servers pushed Sun's revenues through the billion-dollar mark and established the company as a heavyweight rather than a niche vendor. Outside Sun, the message was even louder. RISC wasn't just a nice set of slides from Berkeley. It could own an entire product category. SPARC's commercial success, landing right alongside MIPS-based systems and later HP's PA RISC and IBM's Power Machines, helped trigger the late 80s and 90s wave of risky architectures as every serious vendor scrambled not to be left behind. In 1989, Sun made a move that still looks unusual from today's walled garden perspective. It handed control of the SPARC architecture to an independent trade group, SPARC International. Instead of keeping SPARC as a tightly controlled proprietary ISA, Sun pushed it into an open, non-proprietary, royalty-free model. Anyone willing to sign up could license the architecture, build compatible chips, and submit them for conformance testing. SPARC International owned the trademarks and shepherded the evolution of the spec. Its membership roster included not just Sun, but Fujitsu, Texas Instruments, Cypress, and others. This shifted SPARC from Sun's internal CPU to a broader ecosystem people could invest in without betting everything on a single company's fortunes. Strategically, this did a few things at once. It reassured big customers that SPARC wasn't going to die if Sun had a bad quarter. It encouraged multiple implementations, from Fujitsu's high-end SPARC 64 line to smaller embedded parts, all speaking the same core instruction set. And it positioned SPARC as a kind of open alternative to proprietary RISC designs. In practice, Sun remained the center of gravity for SPARC, but the open licensing helped it spread into niches Sun would never have addressed alone: telecom equipment, embedded controllers, and, later, space-grade processors derived from the ISA. The S in SPARC officially stood for scalable, but this decision made it socially scalable as well. Not just more Windows or more cores, but more companies pushing silicon compatible with the same software stack. By the mid-2000s, the workstation era that had made Sparky's name was already fading. Sun kept building high-end SPARC hardware, culminating in machines like the Ultra 45 of 2006, a two-processor Ultra SPARC 3 workstation the company deliberately over-engineered as a farewell to the desktop line it knew was ending. The real fight had moved to servers, where SPARC's descendants scaled far beyond anything the original Berkeley RISC designers had imagined. Sun's UltraSPARC T1, launched in 2005, packed 8 cores and 32 threads onto a single chip built for throughput computing in data centers, and Fujitsu pushed its own SPARC 64 line even further into Big Iron. Then, in 2010, Oracle acquired Sun Microsystems outright, absorbing SPARC into a company whose business was databases and enterprise software rather than hardware innovation. Oracle kept investing for a while, releasing the SPARC M7 in 2015 with built-in hardware encryption and the M8 in 2017. But on September 1st, 2017, Oracle terminated SPARC chip development entirely, laying off much of the design teams in Austin, Santa Clara, and Burlington after a wave of cuts that had begun the previous year inside Oracle labs. Fujitsu carried the architecture further, shipping an enhanced SPARC M12 server into the early 2020s, but it too has since pivoted its high-end designs toward ARM, and has set an end-of-sale date of 2029 for its SPARC-based Unix servers. Yet the instruction set has not disappeared. Register window-based SPARC cores, in the form of the radiation-hardened Leon processor line developed by Geisler and adopted by the European Space Agency, fly today aboard spacecraft, including the Solar Orbiter, launched in 2020, a design lineage running directly back to the 20,000 gate array chip Sun's engineers built in 1984. Open-source projects have synthesized SPARC cores onto low-cost FPGAs, and Sun's own OpenSPARC release put full processor designs into the public domain years before openness became fashionable in chip design again with RISC-V. What SPARC leaves behind isn't a product line still on store shelves, but a proof of concept that a reduced instruction set, once dismissed as an academic curiosity out of Berkeley, could be scaled credibly from an embedded controller to a mainframe-class server, and that an architecture could be handed to an industry consortium without collapsing into fragmentation. The register windows, the open licensing model, and the sheer range of systems built on one compatible core set a template that later architectures, ARM included, would study closely.